Let's solve another thermodynamic problem involving a heat pump cycle. We have a heat pump that delivers energy by heat transfer to a dwelling at a rate of 11.7 kilowatts. The coefficient of performance of the cycle is 2.8. Determine the power requirement of the cycle in kilowatts, and evaluating electricity at 10 cents per kilowatt hour, determine the cost of electricity during the heating season when the heat pump operates for 1,800 hours. So let's look at a schematic of this heat pump. You'll notice that it looks remarkably like the refrigeration system schematic that we used in our last lesson. In fact, it only differs in the descriptions of what we're calling things. So here we are removing energy from the outdoor air and delivering energy to the indoor space of the house. Now, when this was drawn as a refrigeration system in our last lesson, Q.C was the rate at which we removed energy from the cooled space in the refrigerator, and Q.H was the rate at which energy was delivered to the room air surrounding the refrigerator. Both are operated by delivering power to the heat pump or refrigerator. Now, in this problem, we were given that Q.H was 11.7 kilowatts, and we were given that the coefficient of performance was 2.8. Now, in a refrigeration system, we defined coefficient of performance with the term beta. Here we're using gamma, and that differentiates the COP of the heat pump from the COP of the refrigeration cycle. And the reason we do this is because our interests are different. With the refrigeration cycle, we were interested in cooling the refrigerated space, so we were interested in Q.C. With a heat pump, we are interested in heating the indoor space, so we're interested in Q.H. So let's derive the equations for a heat pump. We'll use our basic energy balance. Delta E is Q minus W. And delta E for cycle is always 0, so 0 is equal Q minus W. But we have multiple heat transfer locations, and so this Q is really the sum of both QC and QH. But we have to pay attention to signs here. QC is positive because it's delivering energy into our system, and QH is taken as a negative because it is removing energy from our system. So we'll say that Q is QC minus QH, and we'll substitute it into this energy balance. And so we have 0 is now QC minus QH minus the work term. And again, we have to be careful of signs. The way, because work is delivering energy into the system, it is a negative term. So here we subtract a negative W. Now I can rearrange this, and I get W as QH minus QC. And that is, this is the third time we've derived this equation. We derived this for a power cycle. We derived the same equation for a refrigeration cycle, and now we're deriving it for a heat pump cycle. We could also derive the same equation only in terms of rates instead of amounts of energy. We could have written our energy balance as the EDT is equal to 0, as Q dot minus W dot, and knowing that the EDT has to be 0 for a steady state system, we will evaluate the same expression. The W dot is Q dot H minus Q dot C, and I'll leave that as an exercise for you to complete. Now we have to define the coefficient of performance, and we have to solve for the power input to this heat pump system. Now the COP is always what we want divided by what it costs us to get it. Well, what we want is we want to heat the indoor space, and that's Q.H. And what it costs us to get it is the power input to the heat pump. Okay, so we want to solve for the power input because that is our unknown in this problem. So that is simply Q.H divided by gamma. And Q.H was 11.7 kilowatts, The COP was given as 2.8. So we know that the power requirement of this heat pump is 4.18 kilowatts. Now we can write an equation for the cost of operating this is the rate of the power input to the heat pump times the time of its operation times the cost per kilowatt hour. And so we have a power rate of 4.18 kilowatts to operate the heat pump, operating it over a period of 1,800 hours at a cost of 10 cents per kilowatt hour. So during that season, this heat pump would cost $752 to operate.